Since I got my mini mill, I've been using an Ikea gooseneck lamp to see what I'm doing, and it works pretty well. I like that it's small and unobtrusive and generates almost no heat, and it's pretty bright. I have a couple of others around the place for the same reason. A particularly good feature is that they're powered from simple linear regulators, so there's no flicker or strobing. Two 7135s drive 250 mA apiece into a forward drop of a little over 3 volts, which is roughly 1.5 watts. So why look for a replacement? Well, they do have a couple of big downsides. The first is the gooseneck has a mind of its own. Second, for filming, it has a really warm colour temperature compared to the other much colder LED lights that I have. And this makes it much more difficult to achieve a consistent look between shots. What I had in mind was to put a car headlight LED ring around the spindle. These days, this idea might seem a bit old hat, but back in 2016, when this project first started, it was still fairly novel. My intention was to fit the LED ring using magnets, something like this. The eBay listing I used gave sizes, but not how they were measured, so I took a guess and ordered the 70mm lights. When they arrived from the Far East a couple of months later, it became clear the dimension quoted was the OD of the board, which meant the ring was a little bit small for what I had in mind. So I ordered a set of 80mm in the hope they'd fit better. They duly arrived after another couple of months, and they were more suitable, but by that time I'd moved on to other things. So all the LEDs were consigned to the stack of paused project tins. You know how it is. Fast forward 6 years and they resurfaced, and I realised it was something I really ought to get finished. Having thought about it a bit more, I realised the work envelope of these small machines is tight enough, without deliberately adding stuff to get in the way. And I wasn't really sold on the magnetic fixing idea either. I mostly cut non-ferrous and plastic, but I do use steel, and the swarf would get drawn to it, well, like a magnet, so I had a bit of a rethink. I'd always assumed the black thing on the bottom of the head was made of cast iron and was somehow important, but as part of replacing a grumbling bearing a while back, I found out it's just a plastic cover. You might be able to guess where I'm going with this. Instead of having the light fit around the plastic cover, I reckoned I could make an entirely new cover that would incorporate the LEDs. A couple of things I might have to consider along the way would be how effective the light would be when using larger diameter tools like a collet chuck or a boring head, and whether I'd need some sort of shroud to reduce the glare and the chances of it getting bashed. A 50mm ring would have been perfect, but that seems to be an unusual size, so I went for 60mm, which is more common and was available with a diffuser. I had a 20mm slice of 3.5-inch aluminium in stock, so that would be the start of the build. Just for a bit of variety, I thought I'd start the whole off with an annular cutter, rather than a drill. After dialing in the aluminium disc, I fitted the cutter in an ER32 collet. I do plan to make a proper holder one day. There's slightly less waste here as the plug from the centre can be reused, rather than the whole thing just turning to swarf. Over on the lathe, I opened out the centre to 43mm, so it was large enough to clear the mill spindle. Next, I needed to add a series of step grooves. The deepest would be to seat the LED ring itself, the next locates the diffuser, and the last provides space to run a bead of low viscosity silicone to seal the assembly against fluid ingress. I marked up the surface to make a stuff-up less likely, as there wouldn't be enough material left to erase a mistake and start over. The next part was a bit of an experiment. I needed some sort of grooving tool, and I figured a round D-bit would give me a head start by having built-in side clearance. I knew I had a couple of pieces of 1/8 high-speed steel sat in the drawer, so I had nothing to lose. I had a feeling that a small cutter that was twice as wide as it was thick might complain a bit, and it didn't disappoint. Now what I should have done at this point was walk away and take a minute to figure out what a better tool might have looked like. If I'd picked the right angles, I could have got better stiffness and clearance at both sides. But instead I battled stubbornly on, resorting to turning the chuck by hand to stop the chatter when the tool was contacting full width. In fairness, it wasn't too bad when it was just nibbling away at the sides. I got there in the end though, and I learnt how not to do it next time. The next thing was to remove some of the spare meat on the OD. I'd also have to waste the middle to accommodate the mounting screws. I kept easing off the feed to break the long strings of swarf before they grew to a dangerous length. I was approaching the size limit of my little machine, and I had to rotate the compound to get enough clearance between the tool and the work. I cut away as much as I dare, and then before I ended up crashing into the chuck, I swapped to internal jaws to bring it to final size from the other side. With the turning complete, I centred the part under the mill and added holes for the fixing screws. I used coordinate drilling rather than the rotary table, as it was quicker to set up. So the ring wouldn't rub on the end of the mill's countershaft, I cut a small relief in the edge. When I offered it up to check the fit, I realised something wasn't quite right. I'd forgotten about the washer on the bottom of the spindle. But a few minutes back on the lathe sorted it. I also realised that the screws I planned to use wouldn't fit in the space I had available, so I made up some fixtures from some bits of scrap to help me modify the screws to suit. I trimmed a few millimetres off the length. I chamfered the raw edge. And I reduced the head diameter. To reprofile the head, I set the compound to put the tool on the back of the job, so I had to run the spindle in reverse. I took really light cuts here, as if the tool had grabbed, it would have unscrewed the work out of the fixture. I made a couple of spares whilst I had the stuff out, as there's no doubt I'd have lost one if I'd only made the 3 I needed. To minimise the chances of the wires getting tangled up on anything, I wanted the power to the LEDs to be as unobtrusive as possible, so I started by removing the existing connections. It was here I first noticed the cutout sections on the edge of the PCB. I'd assumed these were from where tabs had held a circle as part of a larger board during production, but on closer inspection they were actually through-hole vias. They didn't appear to be connected to anything, but I'd have to watch that they didn't cause any shorts when mounted in the aluminium ring. Anyhow, to clear the solder points, I'd need to cut a relief in the front and drill through the side for the wires to exit. Here I plan to make some kind of saddle arrangement with a tube to take the wires safely to the back of the machine, where there's a spare threaded hole that I could pick up to mount some sort of terminal box. To cut the relief for the connections, I set up the rotary table, and after what felt like about 4 hours of fiddling, I got the ring running true on the table and the table running true on the spindle axis. It only dawned on me once I'd finished that for what I was doing there was no need for the work to be central under the spindle. Still, I probably needed the practice. The 4mm slot I'd be cutting would be about 3 times deeper than it is wide, and to stop the cutter from clogging up, I set a fine nozzle of compressed air to help clear the chips. To make the saddle, I took a piece of 3/8 square brass, trued it up on the mill, and reduced the thickness to fit the side of the ring. Whilst I was at it, I cut a scrap of aluminium to the same length to span the other side of the vise. Then I nibbled away at the brass with the boring head. drilled and counterbored holes to take M2 cap heads, and then used the saddle as a template to make the holes in the ring itself. Admittedly, this setup's a bit sketchy, but it only had to withstand drilling two 1.6mm holes, and it was a lot quicker than removing and then retramming the vise. Using a sharpened 3mm rod, I marked out where I would need to drill to take the brass wire protection tube. At this point I took a break from the machining to figure out how I'd power the light. As supplied, the ring was so bright it would likely be annoying, plus I was concerned it might be really overdriven, which would shorten its life. It does come with an inline something, but I imagined it just contained a resistor and perhaps a diode. But when I dug through the potting compound, I was surprised to find a fully formed driver. I managed to find a datasheet on the TP8005, but there was only so much I could get from it. What I could see is that the design was lifted straight from the PDF. As a comparison, I had a look at the driver circuit from one of the larger rings I'd decided not to use, and found this contained a PT4115. Now this one I managed to find an English PDF for, and apart from the maximum supply voltage, it appeared to be identical to the TP8005. Thanks to the datasheet, I could see that the driver featured built-in dimming, which might save me the effort of designing something from scratch. So I did a bit of testing to see if what I'd already got was suitable for what I had in mind. When being driven with 188 mA, the ring has a forward voltage of around 8.4 volts. That's a total power consumption of just 1.6 watts. Now the 60mm ring has a total of 36 LED elements, which means each LED dissipates around 40 milliwatts. In spite of the high brightness, this is much less than I'd imagined, and made me far less concerned about the thing burning out after a few hours' use. Sat on top of the 8.4 volt drive is around 1/3 of a volt of 350 kHz ripple. This frequency is high enough not to cause any flicker issues with the camera, and although this frequency varies with supply voltage, I didn't expect it would cause me any problems. Next I had to play with a dimming function. As I wouldn't be powering it with AC, I could ignore the rectifier on the input. I added a standard 7805 3-terminal regulator and halved its output across a divider made from a fixed resistor and a pot. This gave a stable but variable control voltage of 0 to 2.5 volts, which could be applied to the dim pin of the driver. So far so good. With just a slight modification and suitably housed in a die-cast box, it looked as though the existing regulator would do everything I needed. So I gathered some strip board and a handful of components and built the power supply. I'd not really thought through the wire protection tube at the power supply end, but I soon realised curving the tube would be the easiest solution. I made up a template from soft copper wire and then scanned it in to have a fixed copy that wouldn't get bent out of shape kicking around on the bench. I took a couple of dowel pins and peened the ends so they wouldn't just fall inside, and then fitted them to the tube to help stop the ends from being distorted. Although the S-bend isn't really severe, the thin wall brass tube is really quite stiff, and I was concerned I'd kink it and I'd have to wait for the postman to bring me some more. So I annealed it to give me the best possible chance of it working. I was surprised by just how malleable it became. I decided to anodise the ring. If I'm honest, it was mostly because I've not done any for a while, and I like to keep my hand in. After a thorough degrease in acetone, the ring was moved to a sodium hydroxide bath to etch the surface. Then it went into the acid bath. Having a CAD drawing of the ring made figuring out the surface area for the current calculation much easier. It got 120 minutes at 1100 milliamps. I turned the ring a couple of times to try and make sure that no surface was shielded from the current. The dye bath was next. Finally, it was sealed in boiling water for half an hour or so. I'd give this attempt maybe 8 out of 10. It's pretty even, but the colour isn't perfect. It has a bit of a green tinge to it. I've had excellent blacks from this method and dye before. It might be the particular alloy that I'm using, or more likely the black dye was a little bit weak, as I had to over-dilute it to make the bath deep enough to suit the container I was using. Either way, it doesn't really matter for this project. The time to actually fit the LEDs to the ring had finally come. It was starting to look like the project might actually get finished this time. Even though they don't generate much heat, I used a thermally conductive adhesive to stick the LEDs to the metal ring. The lens was stuck in place with a low viscosity flowable silicone sealant, and once the excess was cleaned up with a cotton bud, it didn't look half bad. I added a drop of soft solder to the wire protection tube before fitting it to the ring. And then it was just a case of fitting everything together. It's been a long time in the making, but it seems to work pretty well. If you were wondering what became of the other LED rings that were the wrong size, well, they won't go to waste. I've used one of them already. And the Ikea goosenecks? Well, I'm not usually sentimental about lamps, but we've had too many adventures to just bin them. So I fashioned a crude reflow plate by fitting a piece of copper into a soldering iron and swapped the warm diodes for cool ones, so they'll continue to be part of the workshop. And I think that's it for this one. Thanks for watching. I hope to see you next time.